Everywhere you look in modern electronics, whether it's renewable energy or giant industrial motors, there's this constant battle going on. Everyone is demanding more power packed into smaller and smaller spaces, and all without wasting a single drop of energy. Well, today we're going to look at a pretty incredible weapon in that fight.
And right at the heart of this whole revolution is a material you've probably been hearing a lot about: silicon carbide, or SiC. Think of it as the foundation that's letting engineers just shatter the old limits of what's possible, leaving traditional silicon pretty much in the dust. And this really gets to the core problem every single power system designer is trying to solve, right? How do you crank up the performance and the power density without basically creating a thermal nightmare? How do you squeeze every last ounce of efficiency out of a system? So here's our game plan for this explainer. We're going to introduce a really cool module, the BAC BMF5040R12KA3. Then we'll peek inside to see what makes it tick. After that, we'll put it to the test in a head-to-head data showdown. And finally, we'll see how it all fits together as a complete solution for designers. All right, enough about the problem. Let's talk about the solution that we're going to be digging into today. And here it is. This is the BMF540R12KI3 from Basic Semiconductor. Now on the outside, it looks like a standard 62mm half-bridge module, a classic building block for high-power stuff. But trust me, what's hiding inside is anything but standard. Okay, let's just get right into the specs, because they tell a heck of a story. This thing can handle 1200 volts and a whopping 540 amps of current. But the number that really gets efficiency experts excited is that on resistance, the RDS on, at just 2.5 milliohms. I mean, that is incredibly low. It means almost no energy gets wasted as heat. And that stray inductance, keeping it under 14 nanohenries, is the secret sauce for super clean, lightning-fast switching.
So you might be asking, how in the world did they get those numbers? Well, it definitely wasn't an accident. Let's pull back the curtain and see the specific engineering choices that make this all possible.
It all starts with the engine of the whole thing, BASIC's third-generation SiC chip. That's what gives you those crazy low switching losses and that low stray inductance. But a powerful engine needs a rock-solid chassis to survive, and that's where the high-performance C3N4 substrate comes in. It's the key to making sure this module holds up in the real world. Yeah, let's talk about that backbone for a second. In these high-power modules, the substrate is under a ton of stress, both from heat and just plain old physics. It's so often the weakest link in the chain. So using silicon nitride, Si3N4 is a total game changer for reliability. I mean, when you put it side by side with the older materials, the difference is just night and day. Look at the bending strength. Si3N4 is literally twice as strong as aluminum nitride. It's just tougher, way less brittle, and so much more resistant to cracking when the module heats up and cools down over and over again. And look, this isn't just some number on a spec sheet. The testing really backs it up. The source material points out that after 1,000 really grueling temperature cycles, other materials can just start to peel apart. But the Si3N4 substrate, it holds together perfectly. Now that is the kind of reliability you need when failure is not an option. Okay, so we've got awesome tech and bulletproof reliability. But how does that actually stack up in a real-world performance test? Well, it's time for the data showdown. We're going to pit this silicon carbide module against the traditional silicon IGBT module with a similar rating. So here are the ground rules for our simulation. We've got the same bus voltage, same phase current, same heat sink temperature. But pay close attention to that crucial difference. We're running the SiC MOSFET at 12 kilohertz. That's double the switching frequency of the IGBT. We're actually pushing it twice as hard just to see what it's made of. And wow, these results speak for themselves. On the left, that's the power loss for our SiC module. On the right, that's the IGBT. Even though it's running at twice the speed, the loss peaks for the SiC module are just so much lower than the IGBTs. All that stuff you see on the right, that's wasted energy, and the SiC module has pretty much eliminated it. So less wasted energy means less heat, right? And here's the proof. The SiC module's internal temperature levels out around 109 degrees Celsius. The IGBT, which is only working half as hard, is already cooking at 129 degrees. That's a 20-degree difference. That's a massive win for thermal performance, and it gives you a huge boost in long-term reliability. So what's the bottom line here? When you add it all up, the numbers are just staggering. The IGBT is wasting about 1,120 watts of power as heat, and the SiC MOSFET, a tiny 243 watts. That's a reduction in power loss of over 78%. And what does all that get you in the end?
It gets you a total system efficiency of 99.39%. You're basically converting every bit of input power into useful output power. That is the holy grail for any power system designer.
Well, let's be real. A fantastic component is only half the battle. You have to be able to actually use it in your design without pulling your hair out.
And BASIC totally gets this. That's why they also offer a dedicated driver and a reference design, the BSRD2503. So this isn't just them selling you a part, it's a whole ecosystem. It's designed to get engineers up and running fast, taking all the guesswork out of the process.
So where does all this amazing performance actually make a difference? Well, pretty much any place where efficiency and power density are king. We're talking more efficient solar inverters that get more power from the sun, smaller and more powerful industrial motor drives, and super reliable energy storage systems that are going to be the backbone of our future electrical grid.
You know, at the end of the day, a technological leap like this isn't just about the component itself. It's about all the new doors it opens. It allows engineers to completely rethink designs that just weren't possible before. So the real question is, with this kind of power and efficiency in your hands, what will you build next?